Perhaps the most recognizable and certainly the most visible part of any electricity transmission system is the towers and wires that wind their way across the land. As populations grow and suburbs expand further and further outwards, the web of the electricity transmission network consumes more and more valuable land, and the costs related to both construction and maintenance of this infrastructure continue to rise dramatically. And concerns don't just centre on the burgeoning costs of these networks. Their impact on both human and animal life, as well as homes, businesses and vital infrastructure, has been witnessed through significant fire events in recent history. None more destructive than the 2009 Black Saturday fires in Victoria.
Many of the people who died on Black Saturday perished while trying to defend their homes. There was a claim that power lines also played a major part.
70% of the deaths approximately that occurred here occurred from electricity asset failures.
The Bushfire Royal Commission found that on the 7th of February 2009, electrical faults caused 5 of the 11 major fires. Cyclones, storms, floods and other weather events can also cause significant damage to transmission infrastructure.
Wild storms have lashed parts of northern Sydney, cutting power and bringing down trees.
The power line damage is quite severe, and electricity companies there say that they in fact will need to do quite a bit of work today, and that power may remain out for quite a few hours yet this morning while they check where the damage has been done.
Not only creating enormous expense to repair and restore, but also the not insignificant risk to emergency services and those with special needs, plus the ensuing inconvenience to affected households and businesses.
Family and friends reunite after a horror 24 hours, and today they learned what caused this devastating blaze. Authorities say it started near power poles. It's believed clashing power lines sparked the fire.
So what is the alternative to our very inefficient electricity transmission infrastructure? Like many groundbreaking discoveries of the past, the answer is provided by nature. Lightning strikes the Earth some 8 million times each and every day, with about 10 return strikes for each event. That means a total of about 80 million actual strikes per day, or close to 1,000 strikes per second. Science has proven that it's routine for lightning to travel up to 10,000 kilometres through the Earth before it dissipates, with no detrimental effects on the environment. Understanding and mimicking this natural energy transfer system is the key to delivering electrical power wirelessly across the planet. The opportunities such as safe, environmentally friendly and inexpensive wireless power transmission system opens up are considerable, especially when it will now become economically viable to wirelessly transmit energy from remote areas where solar power stations or wind farms are most effective. And of course, the bottom line must be the positive impact on electricity bills for everyone. No more costly construction and maintenance, freeing up large tracts of land for other uses, and delivering alternative power generation from remote sources directly to the grid are just some of the economic advantages offered by wireless power transmission. Wireless power transmission, or WPT, is not only possible, it's demonstrable and commercially viable, and offers significant financial benefits to all, especially early adopters.
This is a model of the WPT system. The idea of this model is to actually demonstrate wireless power transmission. The WPT system uses a simple process of transmitting energy through the ground, that is the Earth. In this model, this ball here represents planet Earth. So what we're endeavouring to do here, and what we're actually showing in this model, is how to transmit power from one location, here, in the Earth, in the ground, to another location, here. Now to do that, we have to punch energy into this particular side of it. Once it comes in here, then connects to this point here. To simulate that in this model, we've actually covered the inside of this ball with silver foil or aluminium foil. And by doing that, it means it's conductive between this point and this point. They already do that in a system called SWIR. So this is not new. This is just something that already happens that we're taking advantage of. The difference is now that when we punch power into this point, the power can come out of this point from a single wire, and that's the difference. We only need one conductor. The power then comes through this wire and it runs over here to the bottom of this coil. The power then enters the bottom of the coil and it runs up through the copper wire wrapped on the PVC pipe, and it generates a higher voltage than what you would normally get. Attached to the top of the coil is a ball over here. It's called a capacitor, but what it does, it enables us to tune this to resonance. Well, what resonance does here enables voltage to be low voltage at the bottom and very high voltage at the top. We then take the power off this coil and we put it through these lights. Now these lights are connected up, so it goes into this light, then into this light, then into this light like that. That's called in series. And then it comes back around here. So we actually have a closed loop, and that's all being run by this one wire. If we have one wire running it means we only need one conductor. If we have one conductor, that means we can actually use the earth itself, which is a conductor, to run things over many, many miles. We have power going in this point, we can have power coming out that point, so in between, the electricity just flows backwards and forwards. This is just run by a pair of batteries. There's just two batteries. It runs at 24 volts at this point. There's a small unit over here, that's a resistor, just stops too much current going through the system. This thing here, all this is a switch. So you have two batteries, a wire running around a coil, and that switch. And that causes the DC in the batteries, that's DC power, to become AC power in the transformer at the back. This actual coil here we use as a transmitter. This point here is joined by a copper wire down the bottom, wraps up the top. There's a green wire comes around here and goes round. It's a secondary circuit on the coil. It's run by a primary coil. All this wire does is just measure the voltage at the top. And again, you'll see we've got a sphere up there, it's connected to the coil. That again creates resonance. The idea behind the resonance here is it means in this particular circuit, we run this secondary coil here at a much higher voltage than what it would normally run. By using this coil and using this transformer here, what we can do is instead of running this particular circuit where it would normally run at 240 volts, it now runs at about 1500 volts. It's a combination of two things. We actually resonate this coil, but then we actually put a load on it. So this coil connected to that coil enables the high voltage to be maintained whilst we're running this system. The purpose of the WPT model is to demonstrate wireless power transmission, and so to achieve that I just need to turn it on. Voila!